Hello my dear students, welcome back to Electron Academy. So we are going to again organic session. Now we are in organic sessions. Last class isomerism 1 completed. So today isomerism 2. In isomerism 1 we discussed about the structural isomerism. First 3 we finished. So in this session isomerism part 2. So isomerism part 2, what we have to learn? So see here. Right. So last class what we finished? Chain isomerism, positional isomerism and functional isomerism we finished. So in structural total 6 types na. In last session we finished three things, and remaining isomerisms, 3 isomerism we will discuss in this session. So what is today goal here? Today goal is what? So structural isomerism. In structural isomerism, ring chain isomerism as well as the ring chain isomerism, metamerism, tautomerism. In structural isomerism, ring chain isomerism, metamerism, tautomerism. 3 we will learn in this session. Right. Sir, what is the ring chain isomerism, sir? Ring chain. Ring chain. One ring. First of all, what are the isomers, sir? Again I am repeating, what is isomer? Iso means same. Iso means same. Mer means isomerism. Same molecular formula they are having. Same molecular formula, and one structure will be ring, another structure will be chain. So these are called as the ring chain isomers. What we call ring chain isomers. Sir, what are the ring chain and what examples are what, sir? So what is the given definition will be, if one isomer has open chain structure means end there, terminals we have, for example here we have terminals. So and other has cyclic structures, then isomers are known as the ring chain isomer. So simple here I am underlining the key points here. One having open chain structure, one having open chain structure, another having cyclic structure. One having open chain structure, another having cyclic structure, both are having same molecular formula is called as the ring chain isomerism. Right. Sir, what are the examples, sir? We have first example we are taking here. So alkenes, cycloalkanes. Alkene, double bond is there, and cycloalkane. Alkane means single bonds are there, and as well as the what we call cyclic structure it will be. We know that. Alkenes and cycloalkanes. Sir, what is the molecular formula, sir? Alkenes and cycloalkanes molecular formula is same, that is CnH2n. CnH2n. N number of carbons we have, 2n number of hydrogens we have. So that is called as the alkenes and cycloalkanes. We can make 2 structures. One is the alkene structure, another one will be the cycloalkane structure. Right. So first of all I am taking here, so molecular formula for this C3, if you take 3, this is CnH2n, right. First of all I am taking here C3, 3 carbons we have, C3H6. What is the molecular formula? C3H6. So C3H6 means I am writing here 1, 2, 3. What is the structure for this? Propane. What we call propane. Propane as well as the cyclopropene. Double bond there here, propene. Propene and 1, 2, 3. Cyclopropane. Propene and cyclopropene are collectively called as the, one is a ring, one is a chain. Ring chain. Chain means terminal we have, terminal end there, end carbons we have. One is a ring, another one is a chain. So these are called as the ring chain isomers. What we call ring chain isomers. Example, alkene and cycloalkanes. Alkenes, cycloalkanes. Cyclic means rings. So next, this is the first example for ring chain isomerism. So another type. What is another type here? Alkenes and cycloalkanes here. Alkynes and cycloalkenes. Alkynes. Sir, what is the formula for alkynes, sir? CnH2n minus 2. N number of carbons are there. 2n minus 2 number of hydrogens we have. This is called as the CnH2n minus 2. See, with this formula we have 2 things. Alkyne as well as the cycloalkene. Alkyne as well as the cycloalkenes. So both are collectively called as the, one is a ring, another one is a chain. Ring chain. Ring is one is ring, one is chain is called ring chain isomers. For example, the molecular formula for B C4, 4 2s are 8. 8 minus 2 6, C4H6 formula. C4H6 formula, I am writing alkyne. What I am writing here? Alkyne. This is butane. 1 butane. What I am writing here? 1 butane. And cycloalkene. It is a cyclic ring. Closed. 1, 2, 3, 4. Cycloalkene. One is a chain, one is a ring. One is a chain, one is a ring. This is called as the, what we call here, ring chain isomers. So cyclobutene, this name is what here? Cyclobutene or 1 butane. Cyclobutene, 1 butane. These are called what we call? So ring chain isomer. This is a second example. Sir, what are the ring chain examples, sir? First example is what, sir? First example will be alkene and cycloalkanes. Second example what, sir? Alkynes and cycloalkenes. This is two things. Now, two examples over. Next one. Alkenols, enol, in that name only there. Enol, en means what? Double bond. Ol means what? OH group is there. Enols, alkenols, and cyclic ethers. Cyclic ethers. Ether means ROR. ROR will be the open chain. Ring, inside the ring oxygen there, inside the ring. For example, I am taking this. This is cyclic ether. This is also known as epoxide. This one. Cyclic ethers. These are called cyclic ethers. This is called tetrahydrofuran. Best solvent in organic chemistry. So, right. Cyclic what we call here? So, alkenol. See here for this example. Enol. Why sir enol? Double bond is there en. We know that OH is there. That is a ol. Enol, and we have here CH2, cyclic ether. So both are called as the alkenol and ethers. So these two are called as the ring chain isomers. What is the molecular formula? 3 carbons are there, 6 hydrogens are there, 1 oxygen we have. Same here, 6 hydrogens, 3 carbons, 1 oxygen there. What we call here? So what we call, these two are called as the generally alkenol and cyclic ethers are called as the ring chain isomers. So 3 examples we have. What are they? So tell me again, what are the ring chain isomer examples? First one. So first one will be, what is the first one here? So first one will be alkenes and cycloalkanes. Yes sir. Second one what sir? Alkynes and cycloalkenes. Yes sir. Third one is what? Alkenols and cyclic ethers. So these 3 are collectively called as the ring chain isomers. What isomers? These are called ring chain isomers. Yes sir. So ring chain isomers is crystal clear. Now we are moving to some examples. Some more examples I will explain. So very much important here. So ring chain isomerism examples. Ring chain isomerism example. For example, I am taking, this is a thing. Right. What is this sir? Here 5 carbons we have. 1, 2, 3, 4 and 5. So what is the name of this? 2-pentene. 5 carbons are there, pent, and second position ene there. So 2-pentene. So what do we call here? 2-pentene. Sir, tell me sir, 2-pentene enes. So 2-pentene and so alkenes and cycloalkanes. What are the cycloalkanes here? This is a cycloalkane. Cyclopropane. Cycloprop, not 5 carbons are there, pent. Cyclopentane, not prop here, 5 carbons we have, pentane. Cyclopentane, 2-pentene, ene. Cyclopentane and 2-pentene, these are called as the ring chain isomers. What we call? These are called as the ring chain isomers. Ring chain isomers. A ring, one is a ring, another one is a chain. Ring chain isomers. Is it clear? Right sir. Next number 2. Alkynes we are taking pentane. Otherwise hexane we will take 1, 2, 3, 4, 5, 6 hexane. 6 carbons we have and triple bond at first position, 1 hexane. So 1 hexane and cyclohexene. 1 hexane, these two are having same molecular formula, but one is a chain, one is a ring. These are called as the ring chain isomers. Is it clear students? So ring chain isomerism is clear for you, right? So these 3 examples if you remember, so then ring chain isomerism is very easy. So ring chain isomerism, so crystal clear, we finished. Next we are moving to another isomerism. This is a 5th isomerism, metamerism. Very special it is, and it is confusing also. but in easy way I will explain here. What is a metamerism, sir? What is a metamerism? Simple, I am taking two different compounds which are having similar, I am taking same compounds like ethers we are taking for example. So same molecular formula we have, but so ethers having oxygen, right? Inside the oxygen, left part and right part, the carbon skeleton will be different. So in easy way I will explain with examples. For example, I am taking this is a ether. So this is a ether and this is also ether, both are same. Both ether, what is same? Molecular formula is same. But if you check here, this is the oxygen here, this is the oxygen, middle oxygen we have. Oxygen left side 3 carbons we have, oxygen right side 1 carbon we have. Left side 3 carbons, right side 1 carbon. Now come to this example, left side 2 carbon skeleton, right side 2 carbon skeleton there. So these two are collectively called as the metamerism. Sir, what is a metamerism? Again I am explaining clearly. See, this is a middle oxygen there. Oxygen is a functional group here in ether. So left side 3 carbon chain, right side carbon. Total 4 carbons we have. Left 3, right 1. But here I am arranging left 2, right 2. Symmetrically I am arranging. So these two are same molecular formula, but carbon chain is different. Carbon chain is different around the oxygen, around the functional group. These are called as the metamers. What we call this is called metamers. Metamers. This phenomenon is known as the metamerism. This phenomenon is known as the metamerism. Now next one. So in ethers only, not in ethers. First of all, ether exhibits metamerism. Ether exhibits metamerism. But one important point here. So note. So what is a note here? Minimum ethers exhibits metamerism. Ethers exhibits metamerism. Yes, ethers exhibit the metamerism. So minimum how many carbons required? Minimum 4 carbons required. Minimum how many carbons required? Minimum 4 carbons required. For example, what is the formula for ether? Cn H2n plus 2O. This is a general formula. Cn H2n plus 2O is the general formula for ether. So now what I am taking here, so for example, minimum ether formation 2 carbons required for ether. For ether formation 2 carbons are required. For example, I am taking here C2, 2 2s are for 4 plus 2 6, C2H6O cannot exhibit the metamerism. Next C3 I am taking C3, 3 2s are 6, 6 plus 2 8, C3H8O cannot exhibit the metamerism. From 4 onwards it will be C4, 4 2s are 8, 8 plus 2 10, 4 C5, yes, it exhibits C5, 5 2s are 10, 10 plus 12 exhibits. So minimum 4 carbons there, then only it will exhibit the metamerism. This is about the ethers. Ethers exhibit the metamerism. Not only ethers, second point, but amines also will exhibit. Amines also will exhibit the metamerism. Sir, what amines are? Amines are 3 types. 1 degree amine, 2 degree amine, 3 degree amine. But only 2 degree amines will exhibit the, so what we call metamerism, 2 degree amines. Sir, what are the 2 degree amines? So this is a 2 degree amine beta, 2 degree amine. So nitrogen connected to 2 carbons. Nitrogen is connected to 2 carbons, that is called secondary amine. Here also 2 carbons. Same. What is the metamerism definition? This is a functional group here, NH. This is a functional group here and functional group here. So NH left side, so count the carbons here, 4 carbons count it. Right side how many carbons? 1 carbon there. Left side 4 carbons there, right side 1 carbon there. Here left side 3 carbons we have, right side 2 carbons we have. Left side 3 carbons, right side 2 carbons. So this is called as these two are collectively called as the metamers. Amines, secondary amines also exhibit the metamerism. Next, ketones also exhibit the metamerism. Ketones. Third point is what? Third example, so ketones here, ketones. So what are the ketones, sir? So first example what? Ethers exhibit the metamerism. Second example, secondary amines exhibit the metamerism. So third is what? Ketones also exhibit the metamerism, because this is a ketone. So what is the name of this, sir? First of all you have to count it 1, 2, 3, 4, 5. 5 carbons are there, pent, and second position C double bond over there, 2 pentanone, 2 pentanone, and here 3 pentanone, 2 pentanone, 3 pentanone are what? So these are also metamers. So now I am taking here C double bond over there, here also C double bond over there, but here left side how many carbons we have here? Left side 1 carbon we have. Left side how many carbon we have? 1 carbon. Right side how many carbons we have? 3 carbons we have. Left side 1 carbon, right side 3 carbon. But here left side 2 carbon chain we have, right side also 2 carbon chain we have. So left side 2 carbon chain, right side 2, 2 2 1 3. So these two are called as the same similar molecular formula, but around the C double bond group different carbon skeletons there. So these are called as the metamers. Sir, what examples? What will exhibit the metamerism? Number 1, ethers. Number 2, secondary amines. Number 3, amines. So these three will exhibit the secondary amines, and number 3 is the what is this carbonyl component? In that ketones. Ketones will exhibit this metamerism. Right. Sir, okay sir, in ethers 4 carbons required. Like that in ketones how many required we will check better here. So note 2. So ketones minimum required 5 carbons. Ketones minimum. Ketone minimum requires 5 carbons. So minimum requires here how many carbons here? 5 carbons. 1 2 3 4. Right. Sir, for example, what is a general formula for this? CnH2nO. General formula for ketone will be, ketone general formula will be CnH2nO. Right. So for example, I am taking here C2H4O cannot exhibit the metamerism. C3, 3 2s are 6, not exhibit. C4H8O not exhibit. Minimum 5 carbons required. C5H10O will exhibit the metamerism. C6H10O also will exhibit the metamerism. Understood students? So simple thing here, C2H4O, C3H6 up to 4 carbons ketones cannot exhibit the metamerism. So right. So again I am repeating here, for ethers, very important for competitive exam. Ethers and ketones. Ethers, ketones. So what is a ether generally? General formula for ether will be CnH2n plus 2O. Ketones CnH2nO. Right. In this minimum how many carbons? 3 carbons there, then only it will exhibit the this one. Here how many carbons? 5 carbons. Here 4 carbons. Ether will be CH3O. Yeah, here minimum 4 carbons required here. Here 5 carbons required here. So for example, I am taking this CH3O, CH2, CH2, CH3, CH3 C bond CH2O, CH2, CH3. That's it. These are called as the metamers. Here 4 carbons remember, here 5 carbons remember. So then only it will exhibit the metamers. So this is about the metamerism. This is a 5th part of the structural isomer. In this structure only different means metamers also known as the structural isomerism also. Structural isomerism also. Right. Next one. Next one problem, important problem this one. What is the question given here? Which of the following pairs are metamers? Which of the following pairs are metamers? Simple. For example, I am taking here keto group is there. Yes. Ketones will exhibit students. Yes. Ketones will exhibit the metamerism. Good. So CH3, CH2, CH2, C double bond O, CH3. Left side 3 carbons we have, right side 1 carbon we have. Yes. Left side 2 carbons we have, right side also 2 carbons we have. So what we call, these are called same molecular formula, but carbon skeleton is different around the functional group. These are called as the metamers. First option is the metamer only, right. Next here alcohol we are taking. So right, next one will be alcohols. Right. So alcohols cannot exhibit. right. Alcohols cannot exhibit the metamerism here. So next one, here ether given beta here, ether. Oh, about here 3 carbons we have, here also what we have here, so 3 carbons we have. So here also 3 carbons we have, so this is also not exhibit beta. So D is the all of this given, so these are wrong options, first option will be the correct answer. Right, next one, which type of isomerism possible in ketones? And one more thing here, next, ketones means, for example I am taking this is a, for example I am taking, this is 5 carbons are there, so third position I am giving ketone, that is called 3-pentanone, this is 2-pentanone. So 3-pentanone and 2-pentanone nothing but, so here, right, position isomerism, first one what given, position isomerism, we know that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. What is a position isomerism? Same molecular formula but different in position of the functional group. Here third position we have, here second position we have, so what we call, so this is called as the positional isomerism. Same molecular formula but functional group position is a different. Here where is there, here third position there, here second position there, that's why these ketones are called as the, so ketones. Possible isomerism is position isomerism. Metamerism already we know that, this is also metamers. How can you check here? Left side 2 carbons, right side 2 carbons, here left side 1 carbon, right side 3 carbon around the C double bond O group, these are also known as the metamers, just now we learned. Tautomerism also there, in next we will check. So alpha hydrogen there, so that is shows the tautomerism. In this alpha hydrogens we have, so this is a functional group, here hydrogen we have, so alpha hydrogen there, so we can know that metamerism, tautomerism also present. Next session we will discuss. So which of the isomerism possible ketone means? So all of this is the option. So what is the option? 4 option. Ketones possible isomers are position isomer, metamerism, tautomerism and all of this. All of this is the answer. So this is about the metamerism. So total in structural isomerism, structural isomerism, 5 isomerism completed. Now we are moving to this 6 isomerism. 99% I am expecting questions from this for any competitive exam. Tautomerism is very important and it is somewhat typical also. It is very difficult also. So see this in this. So tautomerism generally also known as this name also there beta. So first of all tautomerism, another names here. So cryptomerism, allotropism, metotrophy. So these 3 another names for this what tautomerism. Sometimes they will give. So which of the following are metotrophies? If you don't know this metotrophy, tautomerism same, so you will lose the marks. So that's why you have to learn about this again, these 3 names also. So metotropy, allotropism and cryptomerism. Right. So simple definition for tautomerism. Simple definition. Tautomers are having similar molecular formula. Common. In isomer nothing but generally having similar molecular formula. They are spontaneously interconvertible. So for example A to B, B to A like this, spontaneously interconvertible, spontaneous, fastly, rapidly interconvertible. Dynamic equilibrium exists. Equilibrium developed here. So what is the equilibrium here? Developed like this we can show equilibrium, forward and backward reaction, forward is there, backward there. So these 3 exist in, so any 2 compounds will show like this, so those are called as the tautomers. Those are called what we call tautomers. This phenomenon is known as the tautomerism. Simple. What is the definition beta? Same molecular formula and the compounds are spontaneously interconvertible and their dynamic equilibrium develops here. So those are called as the tautomers. Right. So examples what sir? What pairs? Tautomeric pairs. Tautomeric pairs. So pakka we will expect one. So many times given. In JEE as well as Neet also they given. Right. So first example will be ketone and enols. Ketone and enol. Aldehyde and enol. Second example, nitro compound and Se-nitro. Oxime or nitroso. Isonitroso also we called here. Lactam, lactim. This is a very special. Lactam, lactim. Enamine, ketimide, enamine, ketimide, enamine and ketimide, right. So these are called as the 6 pairs beta here. So 6 pairs are important. Again I am repeating, listen carefully. Ketone enol, aldehyde enols, nitro Se nitro, oxime nitroso, lactam lactim, enamine ketimide. The 6 examples are tautomeric examples. One by one we will check. So first of all, this is enol. What is here? This is the enol. Sir, why we call enol? Double bond there, en. OH there, ol, enol. What we call enol? Enol become aldehyde. Here dynamic equilibrium developed. So enol converted to aldehyde, aldehyde converted to enol, enol converted to aldehyde, aldehyde converted to enol, enol to aldehyde, aldehyde to enol. So this is called as the tautomers. What we call, these are called tautomers. Dynamic equilibrium, forward, backward, forward, backward, forward, backward. So this is called keto-enol tautomerism. Now I will explain the mechanism. Simple. So this is a acidic hydrogen H plus. It will be breakdown. So it will be shift here. So here you will get the double bond. So now here we will get the double bond, means automatically this carbon having here 5 bonds. So immediately this one will be shifted here, it will become minus, it will become minus. So here minus there means here H plus there, now automatically it will attracted by this. So finally what you will get, so follow with me, CH2 become here CH3, double bond becomes single bond, C double bond O and H as it is H here. So what we call here, this is called as the enol and aldehyde. So these two are pairs are called as the tautomeric pairs, tautomers. What are the tautomers? Enol and aldehyde. Sorry, second example, enol and ketone, same thing, just instead of H I am taking the R group. So here enol, R C double bond O R there means ketone. Same mechanism here, this one will shift here, this one will shift here, it will be cut, here it will be plus, here it will be minus, automatically it will attracted by this, right, and reverse also possible better here. So here one hydrogen shift here, this one will shift here, so this hydrogen again back bonding here, same back. So this is called as the forward reaction as well as the backward reaction. This is a forward, enol converted to ketone is a forward and ketone is converted to enol. This is also known as the, so forward, backward, forward, this is called dynamic equilibrium developed here, second example. And nitrogen containing compounds, forms, example nitro and Se nitro, nitroso or oxime, oximes are the examples. So what is the nitro, sir? NO, here dative bond we have CH3NO2, simply we can write like this, CH3, in examination they will give like this also, CH3NO2, same mechanism. So this one will shifted here, reverse here. So these are called as the generally what we call here, right. So here alpha hydrogen, this is called alpha hydrogen will shift here, this one will shift here, again this hydrogen connected here, you will get the oxime, that's it. So not oxime, Se nitro form. So nitro and Se nitro, same similar here. So this alpha hydrogen shifted here, this one will shift here, it will be minus, here hydrogen will be cut and it will be here, or here also, this is here, this is here, this is here, reverse. So nitroso and oxime form, double bond NOH is called oxime, nitroso, NO is there, nitroso, double bond NOH mean called oxime, nitroso, oxime also another pair for the tautomeric pairs. So 4 over. Now we are moving to fifth, lactam, lactine. So lactam means NHC double bond O, RR group here, like RNHC double bond O R is called lactam. So same here, similar only here, same here, nitrogen will be shift here and this one will become minus. So here this hydrogen is shifted here again. So this is about the simple mechanism, same as for that, same here, this one here shift here, this one will shift here, here it will be minus, here OH will be breakdown, it will be attached here. Simple, lactam become lactine. So this is also another pair for the tautomers. Last one, ketimide become enamine, So what is a ketimide? So CH3, simple here, same thing here. So double bond NH2 here, double bond NH2. So this one will shift here, this one will shift here. Ketimide means here, so NH only, no 4 NH, double bond NH, nitrogen having valency 3. So CH3 CH double bond NH. Same here, mechanism is same. This one will link it here. So here double bond developed and here, same thing here. This one shift here, this one shift here, this hydrogen will be shift here. So this is about the tautomers, lactamide, lactim, ketimide and enamine. These are called as the tautomers. These are called as the tautomers. So again I am repeating, tautomeric pairs are 6. Ketones enols, aldehydes enols, nitro Se nitro, oxime nitroso, lactam lactim, enamine ketimide. So total 6 pairs you have to remember. Pakka you will get one bit. So from this, and another type of questions they will ask like this. So conditions for tautomerism, conditions for, so essential conditions. So to show the tautomeric pairs. So first one, alpha hydrogen having carbonyl shows tautomerism. First one is what? Alpha hydrogen carb. Sir, what is alpha hydrogen, sir? What is mean by alpha hydrogen, sir? Simple. For example, here functional group we have. This is aldehyde or ketone, anything. Functional group we have here. So functional group next carbon is called alpha carbon. Functional group next carbon is called alpha carbon. This is alpha, this is beta, this is gamma, alpha, beta, gamma. So for example, in ketones we are taking. So left side will be alpha, right side will be alpha, left side C double bond over left side whatever here, left side will be alpha, right side alpha, alpha carbon. These are alpha carbon. But what is a condition? Alpha hydrogen having carbonyl shows. Alpha hydrogen means the hydrogen which connected to the alpha carbon. The hydrogen which connected to the alpha carbon is called as this one. So here 2 hydrogens, here beta hydrogens. These are alpha hydrogens. The carbon is alpha carbon. So here 2 alpha hydrogens we have. Here 3 alpha hydrogens, 3 alpha hydrogen. Total 6 alpha hydrogens we have. So alpha hydrogen story is this. So next one, right. So alpha hydrogen containing compounds are show the first condition over. Next one, sir, okay sir, alpha hydrogen is there, sir. So bridged hydrogen there, sir. For example, this is an example. So this is a bridged carbon. Here it is attached to this carbon and this too. This is called bridged. So bridged hydrogen do not consider. It is a very important. Sir, you only said na sir, alpha hydrogen carbonyl shows tautomerism na sir. Here alpha hydrogen only, sir. This is a functional group na. This is alpha hydrogen means no. So this is also you have to note down the point. Why? Because it is unstable. Bridged carbocation is unstable. So this is a rule there. So according to this, so this carbon is unstable. So that's why it cannot leave. So this is alpha hydrogen do not consider any time. Next, amines also cannot show tautomerism. Alpha hydrogen we have simultaneously double bond also we need it. Alpha hydrogen we have simultaneously double bond also node. Amines does not having double bonds. So that's why amine compounds are, for example, I am taking this CH3NO2 will show. CH3NO2 will show the tautomerism. Why? Because CH3 I am writing like this, N double bond O, so dative bond O. But amine I am taking here alpha hydrogen there, but double bonds are not there here. So here like this will be, this one will be like this. So nitro compound will show, but amines cannot show. These 3 points are very important. If you learn these 3 points, total tautomerism is easy. Total tautomerism will be easy, right? So I will give you some compounds. So students tell me first one will show the tautomerism or not. So simple example, what is the question? Alpha hydrogen present or not present, check. And this is the first point. Second point, so bridged alpha hydrogen cannot consider. Bridged alpha hydrogen there cannot consider. So simple thing here, this is a functional group and this is a alpha hydrogen there, yes, it will show the tautomerism. So what it will form? Aldehyde will form the enol. So CH3 becomes CH2 double bond, so O become OH here, that's it. This is enol. Enol aldehydes are the tautomers. That's it. First point is, so first one show the tautomerism. Second one, this is a functional group. So attached carbon is alpha. These are 2 alpha hydrogens we have. So alpha hydrogen there, it will show the tautomerism. Simple, alpha hydrogen check, and it cannot be bridged alpha hydrogen, remember that. This is second example. Third example will show or not show, tell me. Yes, it will show. Why sir? Here this is a functional group. C double bond OH is a functional group. So here alpha position hydrogen we have. What we have? Alpha hydrogen we have. It will form the enol. So these are called keto enol tautomers also. Aldehyde here. So here alpha hydrogen not there here. This is a not carbon valency 4 only. CH3, CH3, CH3. There is no hydrogen here. No hydrogen. Carbon valency 4 only. So it cannot show. Why? Because sir here alpha hydrogen is this. These are beta hydrogens. Sir here hydrogens there means these are beta hydrogen. At alpha position there is no hydrogen. At alpha position there is no hydrogen. These are called as the not form the tautomers. Not form the tautomers. Next students, this one. This is alpha position. This is a functional group. Alpha alpha. Yes. It will show the Tautomerism. Next sir here. This is a functional group. Check here. Left side is there. Yes. Right side is there. Yes. So both are called what beta here? This is called as the. It will show the Tautomerism. Why? Because alpha hydrogen there. Next one. This is sir. Yes. Functional group. Alpha hydrogen there. Yes. It will show the Tautomerism. Yes. Next sir here. This is a functional group. Left side alpha, alpha. These are beta. Beta hydrogens there. There is no alpha. Any hydrogen there here? Alpha hydrogen? No alpha hydrogen. No alpha hydrogen means, so not shows the Tautomerism. Not shows the Tautomerism. Next, ring compound like this. Benzene there. So here no alpha hydrogen here. This is alpha. No alpha hydrogen here. So generally if you remove the ring like this, it will be. So here 4 bonds over 1. Carbon valency 4. 4 bonds over here. No alpha hydrogen. It cannot show the Tautomerism. Here sir, alpha carbon only not there. Alpha carbon only not there. So no alpha hydrogen. So it is also cannot show the Tautomerism. Next, ring compound. So this is alpha position. This is alpha position. Here no alpha hydrogen, but here alpha hydrogen there. So alpha hydrogen present. What we call Tautomerism also present in this. Next example do. Here alpha. This is alpha. Here not there, here there. Alpha hydrogen there means it will show the Tautomerism. Next example, very very important here, cyclic compound. Here 2 hydrogen we have. Why sir here? Hydrogen and hydrogen. So total 4 alpha hydrogens we have. This is alpha, this is alpha. Yes. Sir, how can it will be formed sir? Like this. Right. Here double bond OH. So like this it will be formed. That is enol. So here also 1 hydrogen we have. Here 2 hydrogens we have. Yes. It will show the alpha hydrogen we have nothing but it will show the Tautomerism. It will show the Tautomerism. 15th example will show the Tautomerism. Yes sir. Here alpha hydrogen sir. Sir, how can you write sir here bond line formula means just imagine it is a carbon. Carbon having 4 bonds. 1, 2, 3 bonds over automatically 4th bond will be hydrogen. So now check here. This carbon having 1, 2, 3, 4 bonds over no alpha hydrogens here. This is a no alpha hydrogen. These are cannot show the Tautomerism. Cannot show the Tautomerism. Next, very important, bridged one here. So this is also alpha. This is also alpha. This is a functional group. Sir, alpha hydrogen there means yes. So bridged alpha hydrogen cannot involving. Only these are involving. So yes, Tautomerism exhibit in this. Next hydrogen I am taking here and here and here. So this one cannot participate. Only this one will be participates. It is a bridged one. Bridged one cannot participate. That is a rule. Next here. So bridged alpha hydrogen there, but here there is no alpha hydrogen. No alpha hydrogen. So it cannot show this. Sir, alpha hydrogen there, but bridged alpha hydrogen there. I said the second rule. So bridged alpha hydrogen cannot show this. So these are the very best example in this. Next, enols will form now. So they are asking in JEE especially, they are asking enol content. Enol content. So which of the following having more enol content is there? I will give you the order, you have to check. Aldehyde, ketone, ketoesters, aldehydes, ketones, ketoesters, ketoesters with rings like phenyl rings, PH, CO, CH2, COO, C2H, like this. So diols, diol, Al, ketoaldehydes, diketones. So benzene ring, PH means benzene ring containing with C double bond O groups. You have to remember this order here. So donating group here, electron donating group here. So like this. Next, aromatic ring with C double bond O group there, like this. So Here instead of this there is no electron donating group. So here electron withdrawing group. So what is the final case? Electron withdrawing group is there, electron withdrawing group compounds are there. So that one having more enol content, and one more thing also. So sir, I didn't remember this, sir, I don't know this about this, means you have to check the stability of the enol. If that enol will be stable, so then respective will be enol content will be more. Simple thing, stability you have to check. Stability also we have to check. This is some experimental data. So first one, ketone given, very less enol percentage. Next one, CH3 C double bond O diketone we have. Next, these are the some experimental data. So here, for example, you have to take this here. So what it will be formed beta generally? So keto enol tautomerization we have. So here, what we will get here? Benzene ring we will get here. Okay, so benzene ring form, it will be more stable. So enol percentage also more here. Right. So next question beta, this is which of the following having the highest enol content? Which of the following is the highest enol content? Now I am writing here. So which one having more enol content here? See this. Right. I am writing here. Here two possibilities we have. Sir, what are they, sir? This one OH. This one also OH. This is a first enol formation. This one. How can you write, sir? So first one will become like this, second one will become like this. First one will become like that, right. Right. In this here you will get. So enol content, check the stability for this OH. Next one here, this is a very important one. So first one double bond O become double bond OH. Remember na simple double bond O there na double bond OH. So here also double bond OH. So here also double bond OH. Here benzene ring formation, the aromaticity developed. Aromaticity there, compound will be stable. Compound will be stable means highest enol content. I said na beta. So highest enol content is directly proportional to stability of enol. Stability of enol. So stability of enol, resonance is more here. So more resonance there, more stable here. So compared to here like this. So what is the option, sir? So second option will be the correct one. Second or third? Yes, third option will be the correct one. Again I am saying here benzene ring formation there, it is more aromatic, more stable. So stability of stable enol, highest enol content we have. This is a rule. Next example, which of the following can be exhibit the tautomerism? Tautomerism exhibited in, right, because these are the bridged hydrogens. These are what beta? Bridged hydrogens. So bridged hydrogen there cannot exhibit the tautomerism. First one is not the answer. Next one. So here this is a alpha, this is a functional group, this is a alpha hydrogen. So alpha we have, beta alpha we have. So here no alpha hydrogen, here bridged alpha hydrogen we have, it cannot. Bridged alpha hydrogen cannot consider. Bridged alpha hydrogen cannot consider. So here also yes, two hydrogens we have, here we have. But it one will be bridged, it cannot consider, these two are considered. So only 3 will be the answer, only 3 exhibit the answer. Sir, what is the example, sir? Simple, and how can you remember? Alpha hydrogen there, yes, but bridged alpha hydrogen there, no, you do not consider that. Next one, the last question, this one. So given 3 compounds given, which of the given compounds can exhibit the tautomerism? What is the given question? Which of the given compounds can exhibit the tautomerism? Yes, we have only one formula, alpha hydrogen there are not there, check. First functional group beta, here hydrogens we have, why? Because 2 carbons over, remaining 2 bonds are hydrogens, these 2 are alpha hydrogen, yes, first one will exhibit the tautomerism. Next one here, hydrogen we have and hydrogen we have, this is a functional group, yes, alpha hydrogen there, but here you have to check here. So there is no alpha hydrogen in this, so double bond there you cannot take this side, only that side you have to take. So what is the answer in this? Oh, right. And one more beta, here hydrogen is there, alpha hydrogen is there, yes. 1 and 3 will be, yes, but option there in this, yes, here alpha hydrogen there. Here alpha hydrogen there, here also alpha hydrogen there. Right, here also alpha hydrogen we have. So 3 will be formed beta, but double bond OH will form here. Here also double bond OH will form. right. So what will be the answer in this? Right. So first one, it is having alpha hydrogen. Yes, first one will exhibit. Second one also having alpha hydrogen. Second one also having alpha hydrogen. Yes. So but third one doesn't having alpha hydrogen. So third one cannot show. What will be the answer? 1 and 2. So option C will be the answer. So this is today's session, and till now what we finished beta. So isomerism. So I divided into two parts. Isomerism part 1 session, isomerism part 2 is a session. So total structural isomerism we finished till now. What is the structural isomerism? So in this 6 types we have. Structural isomerism having 6. So chain, position, and functional in first video we finished. In this video, ring chain, Tautomerism as well as the Metamerism we finished. So this session, so structural isomerism completed. Okay. So I will give you some worksheets. So you have to solve that worksheet. Any doubts there, ask again. So this is today's session. So remaining we will continue in next class. Bye bye.